Hello there and welcome back to this video series on control systems. In the past video we have seen the response of a first order system subjected to unit impulse step input, ramp input and impulse input. In this video we'll try to consider a second order system and try to specify the step response of this system. In specific, we see that a second order system could be an underdamped system, critically damped system or overdamped system. I would strongly suggest that you watch videos 007 to 011 which contain details on Laplace transform and a little primer on Laplace transform. Videos 031 to 033 which give a flavor of time response analysis and first order system. Carefully take notes while watching these videos, solve the problems and keep all that material handy while you are watching this video. These poles are obtained by setting denominator equal to 0 and these roots are shown here, one with the positive sign and one with the negative sign. The quantity in the square root b square minus 4jk is called the discriminant, and we know that if the discriminant is less than 0 we get imaginary roots. If the discriminant is equal to 0 we get real repeated roots, and if the discriminant is greater than 0 we get real and distinct roots. In case 1 we call it an underdamped system. In case 2 we call it critically damped system. In case 3 we call it overdamped system. To generalize, we write the transfer function as given here, that is, divide both the numerator and denominator by j. We see that there are two quantities. One is b over j as given here, second is k over j given here. These two quantities in fact completely describe the system. We further make a substitution. Omega n is under square root k over j and epsilon is b over 2 root jk. These two quantities completely describe the second order system. If these two are specified, we can say completely all the aspects of response of a second order system. This omega n is called the natural frequency and this epsilon is called the damping ratio, b over 2 root jk. This 2 root jk is called critical damping. So this damping ratio is b over b critical. With that said, we will categorize the second order system response into three types. When epsilon is less than 1, you have these are the roots, and we say that the system is underdamped system which exhibits oscillatory response. It shows overshoot and undershoot. If epsilon is equal to 1, both the roots are the same and both of them are minus omega n, and we call critically damped system. And critically damped system is non-oscillatory. It kind of gives the fastest non-oscillatory response. Then if epsilon greater than 1, the system is overdamped. Both the roots are real and distinct. The system exhibits non-oscillatory behavior. And if this damping ratio epsilon is much greater than 1, the response is sluggish. The system moves very slowly. In the following slides, we will see the step response of a second order system, second order underdamped system, because we have this damping ratio less than 1. Okay. We know that if the input is unit step input, Rs is us of t, then you have Rt is us of t. You have its Laplace transform is 1 over s. Okay, if this is the transfer function of the second order system, then you have Laplace transform of the output C of s is given by this transfer function multiplied by 1 over s. To further find the response terms, we split it into partial fractions as given here. Okay, a by s plus bs plus c by this quantity under denominator. You see that these coefficients a, b, c are obtained by setting s square terms equal on either side, s term equal on either side, and constant term on either side to find a, b, c, these constants given here. With the constants specified, you have Laplace transform of the output given here for convenience, and to find the inverse transform, we write them here. Taking inverse transform on either side, we write the response C of t as this. In this, omega d is the damped natural frequency, which is omega n multiplied by the quantity under root 1 minus epsilon square. To obtain a more compact notation, we simplify the previous expression, that is, divide this entire quantity after 1 minus by under square root 1 minus epsilon square. You have epsilon square here and epsilon here. If you consider this to be sine phi, this will automatically be cos phi. So sine phi multiplied by cos something, cos phi sine. This is indicative of the sine a plus b formula, and thus we get this response to be something like this. This omega d, we already said, is damped natural frequency. Because you have an exponential term with negative, the response kind of decays. Okay, so as time t tends to infinity, this whole term goes to 0 because you have a negative sign here. But before that happens, the response is oscillatory. So in some sense, this is indicative of an amplitude modulated sine wave, where the amplitude gradually goes down to 0. This response we'll see in a graph in a little bit. Firstly, we see that if epsilon is very small, epsilon given here is very small, this term vanishes and this term is cos omega dt, and this term is 1, this term is 1. So you are left with 1 minus cos omega dt. Since cosine of a time dependent function is oscillatory with constant amplitude, this when epsilon tends to 0, see this output is oscillatory, your sustained oscillations. We also see that if time t tends to 0, okay, this output is 1. That's very clearly seen here. If t tends to infinity, this whole term goes to 0 because exponential of a negative quantity as time t tends to 0 is tends to 0. So you are left with Ct is equal to 1. So we say that the error tends to 0. When we say error, it is the difference between Rt and C of t. Okay, tends to 0. And we can also see that when epsilon, the damping ratio, is within the range 0.5 to 0.8, we get very fast response, maybe much faster or comparable to critically damped or over damped systems. And in this context, we say that if two systems have same damping ratio but different omega n, they show the same peak overshoot. We'll define what we mean by peak overshoot, and derive an expression for it. Such systems in general may be said to have the same relative stability. We are ahead of time when we use the word stability. We'll try to define it in some of the subsequent slides. This plot shows the response of second order system subjected to unit step input. We have shown several damping ratios. This is damping ratio 0, and for 0.3, 0.6, 0.9, 1.2, 1.6, and 2, 2.4, and so on. Okay. As we have discussed, when epsilon is equal to 0, you get a cosine oscillation. When epsilon is less than 1, the behavior is kind of oscillatory. You can see that it's going up, coming down, going up, coming down, and so on. This behavior is what we say oscillatory, amplitude modulated sinusoid. Whereas when epsilon greater than or equal to 1, there are no oscillations at all. Okay. I think we can give summary right now. We saw that a second order system can be an underdamped system, a critically damped system, and an overdamped system. And we saw that when damping is less, the system is more oscillatory. When damping is 0, damping ratio is 0, the oscillations continue for a very long time, if not forever. And when epsilon is in this range, or even otherwise, limit as t tends to infinity, Ct is 1 and the error is 0. I think that's all we have for now. Have a great day.